Hi, and welcome to Dr. V's Chemistry Webcast. In this webcast, I'm going to talk about the work done by Ernest Rutherford in the experiments that he carried out that eventually led to a revised atomic model. Rutherford was a really interesting character. He grew up in New Zealand, where he had studied mathematics, and after finishing his master's degree in New Zealand, he ended up winning a scholarship and going to Cambridge University to study physics with J.J. Thomson. Oh, okay, that's a big deal, right? After he finished his degree at Cambridge, he started his own research projects. One of the things he got really interested in was radioactivity. And in fact, he discovered alpha particles, which are emitted in radioactive decay, and beta particles, which are emitted in radioactive decay. And in fact, that led to him winning the Nobel Prize. And he had a very successful long-term career. And eventually, when Thomson retired, he actually took over Thomson's position at Cambridge University. But he was at a few other institutions before that. And so one day, Rutherford woke up and said, hey, Thomson has proposed a new model of the atom, the first model of the atom. Let's test it, okay? I think I've got a way to do it. So Thomson's model, as you may recall, was called the Plum pudding model, and it had negative electrons embedded in a sphere of positive charge that's kind of diffuse. The positive charge is just sort of all around. I always think of that positive charge as sort of goo-like. That's the technical term, but it'll work. All right, so he came up with an experiment to test this. Here's what he said. All right, on the next slide. Let's take a radioactive source of alpha particles and shoot them at gold foil. Now, alpha particles, as I had mentioned, were something Rutherford had discovered, that certain radioactive materials emit these particles that were called alpha particles as they decay. And what we know about alpha particles is that they're really quite massive, many, many, many times more massive than an electron. And they were positively charged. So they're really massive and positively charged. Now we know that they're the nucleus of a helium atom, but that wasn't recognized at the time. So he's setting it up so that we're going to make a beam of these alpha particles and direct them at a piece of gold foil. The gold foil was so thin it was almost transparent. And then we could follow where the alpha particles went after they hit the gold foil, because they would hit the screen that surrounded them, which is shown here in green. And the fluorescent screen would literally light up when an alpha particle hit it. So we have an idea, they said. If Thomson's model is correct, what should the alpha particles do? They said, well, we've got this diffuse positive charge, and then we've got these little teeny tiny electrons. So if we're throwing big, giant positive particles at them, they should go straight through, right? Because that positive charge in the Thomson plum pudding model doesn't have much to it, so they should go straight through. Maybe they'll bounce off occasionally if they manage to hit an electron, but otherwise we're expecting just smooth sailing there. So they start to do the experiments. Here's another diagram of the setup. So really, all of them were expected to just go straight through. So, here's a photograph of Rutherford in the lab with Hans Geiger, who was one of the students who helped run the experiments, along with Hans Marsden. And they thought it was going to take one summer, and it was like 3 years of work to get all this done. So we talk about it as the gold foil experiment, as if it's one experiment, but it was really a series of many, many, many experiments with different metals as well. And what did they observe? Well, they start collecting data, and most of the alpha particles do go straight through. Every once in a while, one would bounce off to the side, and then what really surprised them was that for a very tiny fraction of alpha particles would actually come back at them. They called that backscattering. They're like, whoa, that's weird. And they would do the experiments again and again and again to make sure that they weren't doing something strange or doing something wrong, to really be confident in their results. So most of the particles did go straight through. But how can you explain them bouncing off at angles? How can you explain the alpha particles bouncing back in this backscattering if Thomson's model is correct? So, right, most did go straight through the foil, but that backscattering can't be explained by Thomson's model. Thomson's model is not holding up to the new evidence. What does that mean? If your model doesn't hold up, it doesn't support or be consistent with new evidence, you change the model. And that's exactly what Rutherford did. So he took Thomson's model, who had been his PhD advisor, and changed it. So here's what he thought. Why are they bouncing back? Well, sometimes the alpha particles must hit something hard and dense, and that's what makes them bounce backwards. And if they glance it, they might go off at an angle, but mostly they're going through empty space. So we've got a brand new model, and we can explain these results if we have a different model of the atom. So there must be something hard and dense in the center of the atom. So Rutherford's new model is a nuclear model of the atom. Most of the mass and positive charge of the atom is concentrated in the center of the atom, which we call the nucleus. So we knew the nucleus was positively charged, and then they started looking at mass ratios. It was the 1920s when they really authoritatively identified subatomic particles called protons. Those are in the nucleus. So we've got experimental evidence of protons. We know they're in the nucleus. After more experimentation, they realized the protons themselves didn't have enough mass to account for all the mass of the nucleus. So they proposed that there was another particle in the nucleus called the neutron. Those took a little longer to discover. But most of the mass in the atom is in the nucleus. The atomic number of the element is defined now as the number of protons. We know that correlates to the charge of the nucleus. And the neutrons were eventually discovered in 1932 by James Chadwick, who was working with Rutherford. And it took a while because the neutrons being neutral and not having any charge, it made it a little harder to detect them. But they did eventually get there. So we know protons and neutrons are in the nucleus. The electrons are still in the atom as well, but they're outside of the nucleus. All right, most of the atom is empty space. This is a weird idea when you think about it. All right, most of the volume of an atom is due to the electrons, and the electrons are just arranged outside the nucleus somehow. We're not going to specify that right now. Rutherford wasn't really sure. We just know they're outside of the nucleus, and they're taking up most of the volume. All right, we also know that because atoms are electrically neutral, if I have a certain number of protons in the nucleus, I must have that number of electrons in the neutral atom. I can gain and lose electrons to form ions, but let's focus on the neutral atoms right now. So we've got this new model of an atom, the nucleus with most of the mass inside, and then the electrons outside taking up most of the volume. So, big picture here. Rutherford's gold foil experiments resulted in the concept of an atomic nucleus, the nuclear atom. So, nuclear charge focus in the center, electrons outside. This picture is not to scale, by the way, right? The nucleus is very tiny compared to the volume of the atom, but the idea of the arrangement, the protons and the neutrons in the nucleus and electrons are outside. So this is a good stopping point. We're going to end here.